introduce Sudipan, who actually did a PhD on change detection in Toronto under the supervision of Dr. Francesca Bovolo and Professor Lorenzo Bozzone. And this year, he joined us as a postdoctoral researcher, and will continue working on unsupervised learning for time series data analysis, which is also the topic of today's talk. So Sudipan, the floor is yours. And yeah.
Thank you, Shaoxiang, for introducing me. So I will start with my presentation on unsupervised deep learning for multi-temporal analysis. In this presentation, first, I will briefly introduce to you why unsupervised multi-temporal analysis and why deep learning. Then I will briefly present to you some methods on change detection methods, which involves 2 images. Following this, some methods on time series analysis, which involves more than 2 images. And finally, I will conclude this presentation with some comments on future directions. So to start with the multi-temporal image analysis, I will very quickly go through this. The multi-temporal image analysis we can define as the analysis of images or objects taken at the same place at the different times, right? And in the last decade, we have seen an increased interest in multi-temporal image analysis due to increased space mission, which has provided us with better temporal resolution, and also other reasons like free data access policies, like European Space Agency's Copernicus mission. When we think of the multi-temporal image analysis, the most important aspect of multi-temporal image analysis is change detection, which is between 2 images, like we see over here, between the pre-change image and the post-change image. Even when we analyze more than 2 images, that is n number of images, most of the methods are somehow dependent on change detection, like the methods like change detection, CDM, change detection matrix, they detect change over 2 images, and then they try to capture the time series information over a matrix. So considering the importance of the change detection in multi-temporal image analysis, in this presentation, a large part will be on change detection. Now let's just quickly go through like what can be the applications of multi-temporal image analysis. It can be in environmental monitoring, it can be infrastructure monitoring, mining, and lot other, including even in planetary operations. Right now we see, as you can see in this paper from 2019. And when we just think of one of these applications like environmental monitoring, and we want to go more deep into this, we can say it can be like change in forest cover or urban area monitoring or vegetation change or glacier surface change. So what we see is like change detection or the multi-temporal image analysis can have like a varied application. On the other hand, multi-temporal image analysis is conducted using different modalities of sensor, like multispectral images, hyperspectral images, SAR images, even in some cases also with the LiDAR. And in addition to the modalities, also it's covered with the different resolution, starting from 0.5 meter per pixel to hundreds of meter per pixel. So when we see like this huge range of applications and the modalities, the question that comes into our mind is like, is supervision possible? Some fields of the machine learning where it's supervised learning is a kind of norm, but is supervision possible in multi-temporal image analysis? Of course, there are some methods, supervised methods, like those based on the Siamese networks. However, we have to understand that in the context of the multi-temporal image analysis, collecting level dataset is very difficult. And even if we collect some level dataset, we face several issues, like including generalization to new task or generalization to new area. Like if we collect a dataset in an urban area of Europe, most probably it's not applicable in an urban area of Asia. And sometimes, like in disaster management, it's quite impractical to collect pre-change and the post-change image. Considering all those reasons, traditionally in the change detection and also multi-temporal time series analysis, unsupervised methods are preferred. So let's talk a bit about the traditional unsupervised methods. The traditional unsupervised methods has been generally based on differencing, like change vector analysis and its many variants, or clustering. However, these methods, whether differencing or clustering, they operate on the pixel values or on the shallow features computed from the pixels. In the last 10 years, we see a lot of object-based variants of them. However, most of them try to introduce object-based notion into using simple concepts like superpixels. We have to understand that in the last decade, a lot number of the high resolution sensors have been launched. And with the launch of this higher resolution, which includes, of course, not just spatial resolution, also the temporal resolution, we have higher spatial complexity and also higher temporal complexity. This kind of object-based notions like superpixels, they have limited capability to capture the spatial context and the temporal complexity of the new generation sensors. So when we think of this complexity, the spatial complexity and the temporal complexity, one thing that comes into our mind, of course, is probably deep learning has all the attributes which we need to resolve these issues. That is to capture the spatial complexity, to capture the temporal context. However, deep learning generally traditionally is a supervised method, right? So how do we apply deep learning in unsupervised multi-temporal analysis? That is the question. So before coming to answer of this, let me ask you another question. Do deep features generalize from everyday objects to remote sensing and aerial scene domains? Well, this is not just a question. This is, in fact, a 2015 paper that introduced transfer learning to remote sensing. So, of course, our obvious answer is transfer learning. How we can introduce deep learning in the unsupervised multi-temporal analysis. However, transfer learning is just a starting point. When we see in the machine learning and the computer vision literature, we see in the last few years, we see a kind of evolution of the unsupervised or semi-supervised or self-supervised deep learning. Here are just some of the terms over this that covers this evolution, like transfer learning, generative adversarial network, deep clustering, graph convolutional network. There were some more keywords also regarding this. However, the most interesting phenomena is this. In the last few years, we saw that as this unsupervised deep learning literature evolved, the unsupervised multi-temporal analysis methods also co-evolved with this above evolution. So let's see how this evolution happened. Towards this, I will start with a change detection method, which is unsupervised deep change vector analysis, or DCVA, for very high resolution optical images. So before introducing the method, let me briefly talk about the label again, as we're discussing. So I told you already before that collecting multi-temporal level is difficult. Why is it difficult? Because multi-temporal level, when we think about multi-temporal level, it's pixel-wise label, collected as labeled as change or unchanged, or labeled as maybe with more details like change of type 1, change of type 2. So it's not just a level over one image, rather a level over two image, which is much more difficult than collecting labels in the image classification or the semantic segmentation, where the labels are just over one image, right? Like it's just one image. Label can be building water or something else, or the pixels in the image, which is a bit more difficult, but still easier than the multi-temporal label, right? So now I will start with the introduction of the deep change vector analysis. So what's like for the deep change vector analysis, we set up our goal to propose a change detection method employing convolutional neural network for very high resolution optical bitemporal images. That is, given input bitemporal very high resolution images acquired in this work, we make the assumption that they're acquired using the same sensor to devise change detection technique for distinguishing the change pixels from the unchanged ones, which we call binary change detection. And once we have the change pixels, to further segregate the change pixels into different kinds, which we call as multiple change detection. So here we make a very important assumption that we have a network pre-trained on the very high resolution optical images, that is our target images, either for classification or segmentation. So we are talking like about a network pre-trained. However, we are talking network pre-trained for classification or segmentation, not for multi-temporal image analysis, which is very important here. So this is the framework of our method. Given two images, X1 and X2, we use the pre-trained network, which we are talking about just now, to obtain features from both the images, deep features from both the images, F1 and F2, let's say. Once we have these deep features, we can obtain deep feature differencing to obtain the deep change vector, G, which we can analyze using a deep change vector analysis method to obtain the change detection map consisting of the unchanged pixel and different kinds of change pixels. So in this framework, we see that there is a CNN-based part and there is a change vector analysis-based part, which is taken from the remote sensing literature. So now let me go into the more details. First, I will start with the CNN-based part, that is the deep feature extraction part. So in this particular work, for the deep feature extraction, a network is chosen, which is pre-trained for the semantic segmentation on Potsdam dataset, which is a semantic segmentation dataset. Features are selected from selected convolution, deconvolution layers, and features from the different layers are stacked to form hypercolumn to obtain multi-scale representation of the multi-temporal information. And finally, there is also a variance-based strategy to select the features that emphasize change information. So to give you a bit better picture of what I'm talking about, let's say these are the layers from the convolutional neural network. We can take feature from the different layers. We can spatially interpolate them to the same size as the image. Then we can select the subset of the features. We can aggregate them and obtain the deep hypercolumn, which gives us a multi-scale representation of the change information. So once we have this, we can obtain the deep feature differencing to obtain the deep change vector, and we can now go for the change detection. That is first binary change detection using a magnitude-based analysis. And once we have the information from the binary change detection of the change pixels, we can feed this to the multiple change detection, and we can obtain a direction-based analysis to obtain the different kinds of changes. So to give you a bit more details of how this part is obtained, this part contains two parts: binary change detection, multiple change detection. So for the binary change detection, just as I mentioned, a magnitude-based analysis is used. For the magnitude-based analysis, we need to determine a threshold between the change pixels and the unchanged pixels, for which any suitable algorithm can be used, like ARTSO or adaptive. In practice, depending on your application area, you can choose the threshold. If you go through I will not go into the details here, but if you go through the paper, there are some guidelines, or also in the GitHub page corresponding to the deep change vector analysis, there are some guidelines about which one to choose according to your application. Once you have the information from the binary change detection, the deep change vectors, deep change hypervectors corresponding, that is the G's corresponding only to these change pixels, can be analyzed again to obtain the multiple change information. However, we have to understand this G is like a high dimensional vector, right? Because this is what we stacked from the different layers of the CNN. And high dimensional vectors are not trivial to cluster. So what we do is we binarize the deep change vector and we proceed with an iterative hierarchical clustering. I will not go into the very details of this clustering over here. However, this is a very interesting method. I will suggest you to go through the paper to know more details about this. Finally, to show you some result about this, this is result on worldview dataset containing an urban area of Italy, taken with 0.5 meter per pixel. It shows urban complexity, and moreover, it shows the images pre-change and post-change image in different season and with a different acquisition angle, with an acquisition angle difference of more than 6 degrees. However, when we see like this is a reference map and this is a result from our proposed method and some state-of-the-art methods, we see that this deep change vector analysis obtains the object shape, change object shape much more accurately. I will not go into the quantitative evaluation much over here, just for the sake of brevity. And to give you a big picture about the multiple change detection, this deep change vector analysis also is also able to obtain the multiple change detection result quite satisfactorily. So what we saw in the deep change vector analysis is that deep change vectors are used to model the spatial context information. And the deep change vector analysis, this is unsupervised. Why unsupervised? Because no multi-temporal level has been used anywhere. Of course, a pre-trained network has been used, but the pre-trained network is trained for classification or segmentation. This is not trained for any kind of multi-temporal data. However, it is yet robust to the differences in the acquisition angle and the seasons. Now, before going to the next one, let me show you like some facts just to summarize this one. Some facts about this. What we saw the model change detection method proposed for the optical very high resolution image. There was no multi-temporal supervision required. Pre-trained network was required. Is it applicable to time series? Of course, but we will need modeling like change detection matrix. Now, going to our next one, that is extending the deep change vector analysis for Sentinel-2 images or any other sensors which share similar characteristics as Sentinel-2. Why are these kind of sensors interesting? Because they provide a good compromise between the spatial, temporal, and the spectral resolution. However, they show many spectral channels, right? Most of the unsupervised methods in the literature, they have limited capability to exploit such images, and they generally make assumption and use application-specific indices like NDVI or something like that. And this is the interesting part of this work here. First assumption is, of course, unsupervised. But second assumption that is that this work was done on a based of assumption of being band agnostic. That is, no application-specific selection of the band was done. All the bands except 60 meters were used, which is like, of course, like a kind of disadvantage if you already know the application you are using it. But okay, we wanted to operate under this assumption to see like what is the limit of our method. So first challenge is like there was no pre-trained network available for the Sentinel-2 images or this kind of images, and then there was like a large number of bands which I'm talking about here. So first, to solve the first one, that is no pre-trained network, what we did that we used Euroset dataset and we used auxiliary classifier GAN to train network, and then we reuse the discriminator as feature extractor in the deep change vector analysis framework. Rather than this, the more interesting part is this one, that is a large number of the bands, how we deal with this. So to deal with the large number of bands in a semantically meaningful way, what we do is we grouped the bands into different groups of spectrally similar bands like RGB, SWIR, NIR, and this is like the vegetation red edge bands. So we grouped them into 4 different groups. We did the deep change vector analysis on each part separately, which means over here, let to make clear that this training was also done on these 4 groups separately. So then we had like 4 deep feature extractor corresponding to each of them. And after this part, okay, we do a feature selection, we concatenate all the features from all these 4 groups, RGB and all these 4, and then okay, there is a deep change vector analysis part. To make To make clear, of course, if you know the application beforehand, if you want, you can exclude one or two of this band grouping from your analysis. However, the result that I'm going to show you next, we used all the four, which is a kind of disadvantage, right? Here is some result on alpine burnt area. We show the reference map, the proposed method, which outperforms the state-of-the-art methods and obtains much better object shape. And also we see the same for an agricultural area over here. There is also an evaluation on an urban area, urban data set, which I will mention later. I'm just saying now, but I will mention later about this evaluation. Okay. So before proceeding to the next task, let me summarize what we did here. It's same like before. We use sensor resolution of high, not very high. We use pre-trained network. However, this time this pre-trained network was trained by us. Now going to the third one, the building change detection in the very high resolution SAR images. We are moving to the active sensor. The methodological flow is more or less same. There are some details here and there which I will not go into over here. That is okay. To summarize, we have a CNN based part, we have a change vector analysis based part, and then there is a part on the fuzzy building detection, which is taken from the literature of the building change detection. Not going into this one or this one, I'll rather focus on this part where we did not have a deep feature extractor available and how we trained it. So what we did is, since obtaining large scale leveled SAR dataset is difficult, right? Because it's not so trivial to level the SAR images. They are not visually like something prominent. However, it is much easier to obtain paired SAR and optical images. So we used SAR optical dataset, which is unlabeled, to train cycle GALE, consisting of two generator, two discriminator. And we make assumption that these generators learn useful semantic features while trying to learn the multimodal transcoding. Once this training is done, we use a generator as a deep feature extractor in our DCVA framework over here. Over here, we use this as a this generator as a deep feature extractor. So this is the novelty here in terms of deep learning. There are some other details of which I will not go here. If you are interested, you can always read the paper. This is an result shown on an area of earthquake in Italy. We see like this can, the proposed method can capture the destroyed buildings quite accurately. So to summarize, what is the key point here? The key point here is that we still use pre-trained network as a deep feature extractor. However, this pre-trained network training now doesn't require any kind of level, like not even a level for image classification. Like in the first task, we saw about some network which is trained on Potsdam dataset. Second task, something trained on the Euroset, but this one, okay, trained on something which did not require any label as such. Now, let me talk about semi-supervised change detection, how we can do it. So what is semi-supervised change detection? Like sometimes in a large scene, we can have few labeled pixels scattered over the scene, right? So this I will not go into the very details, just to give you a bit of hints how it is solved. The graph convolutional network is very useful in this kind of scenario where few label pixels are available over the large scene. So we use the graph convolutional network. However, before this, there is a part on the representing the scene as superpixels or parcel, we say, because it's a multi-level superpixel. Since like, okay, you can also fit the input image as pixels to the graph. However, that is not efficient in terms of memory, and also like pixels doesn't capture the object-based information. So okay, we go for the superpixel segmentation. We capture the object-based information, then we fit to a graph convolutional network. I will not go into the more details of this. Okay, these four methods over here, the first three were based on deep change vector analysis, and the last one is not, is based on GCN. These were the change detection methods. Now let me talk a bit about the time series analysis method. So time series analysis method, first one I will talk is unsupervised deep joint segmentation of multi-temporal images. So this, rather than change detection, I'm talking about joint segmentation. That is, given T images, given a series of images x1, x2, xt, we want to obtain segmentation map C1, C2, C3. Our assumptions are same again, that we are going to do it in an unsupervised way without using any kind of label. We want to be able to capture, like deal with the semantically meaningful level, and this proposed method should be capable of assigning same level to the pixel in the same location in the different times. So how we do this? Here comes into picture deep clustering. Like as I told you before, like different terms in the deep unsupervised deep learning, transfer learning, then graph convolutional network, then a generative adversarial network. Then here comes another one, deep clustering. So given T images, we pass it through a set of trainable convolutional layers, which you can initialize in any way that you want. We obtain a deep feature representation. We obtain label from the last layer using argmax classification of the final layer. And once we have this, we can calculate a loss between these two. And we can use this loss to train these convolutional layers. And we can repeat this process in a kind of iterative way. So what we say, this process is like self-leveling via simultaneous level assignment and representation learning. In this way, it's able to learn both semantic consistency and temporal consistency over the images. So here we show you some result, which is over the Munich city, over 4 seasons. This is a reference urban area. And this is the segmentation map, binary segmentation map obtained by this proposed method, which we see like captures urban area quite accurately as far as an unsupervised method is concerned. Now there comes another more interesting part, is like once you have this network train, you can also use it for change detection. How? One very trivial way, of course, can be to just subtract this segmentation map. However, that doesn't work very well. The better way is to take out this network after training and use it in the deep change vector analysis framework again as feature extractor. So in this way, you can do the change detection. And interesting thing is this way of doing, like taking the self-supervised network and using it in the deep change vector analysis framework gives very good result in some scenario, not all, in some scenario. Like the previous Sentinel-2 approach I was showing on a urban area data set, which has been launched a couple of years back, gives us like a sensitivity and specificity score of this, whereas this approach that I'm talking now, like taking this network out and feeding this to these images, gives a much improved result on this data set. So this is very good over some of the areas, more specifically over the medium resolution ones. Now coming to the weight, let's check the facts here again. We use the pretrained network here. However, pretrained network did not require any level. Is this applicable to time series? Yes, this is also applicable to time series without doing any kind of modeling like change detection matrix or anything. Now, the very last part of this presentation, that is unsupervised time series analysis by learning to reorder, which is inspired from the video analysis literature. So what I'm talking, like generally the time series, even if there are, let's say, some seasonal changes or something like that, generally the time series where the pixels are unchanged, they all follow a natural order. So what we can do is we can jumble up the temporal data in random order, and then we can learn to rearrange. So how we can do it? Let's say we want to detect change over the a series of images, x1, x2, xt, and also we have another series of images z1, z2, zt, which is acquired over an area having similar geography over S, however not impacted by this change that we are interested here. So first we can use this z1, z2, zt. There is a deep feature extraction part. Okay, let's skip this, but the main part is here, like we do a time series sequence shuffle, and then we learn to reorder it back based on the assumption that unchanged sequence follows a natural order. Unchanged or even something with seasonal change is fine here. That will come as unchanged over here. Then when we apply this, our target area over here, x1, x2, xt, with the same model that is used here. When we use it here, bring it here and try to reorder it back, the unchanged pixels will be reordered back, but the changed pixel won't be, because the change sequence defies that natural order which is present in the unchanged sequence. So for this, I will not go into the details of showing you any result. However, this method has been evaluated over a time series of 7 images and another of 5 images. We can, of course, also see over more. So right now, to conclude my presentation, let's just talk a bit about what is next. So first thing is this is from few slides back, we saw the unsupervised joint segmentation using T images, right? And I showed you some result on Munich city. So the question is is my self-supervised model learned on Munich? Is it directly applicable to London without doing any kind of further adaptation? This comes us into the more general question, that is, given a model trained on a big data set, can we adapt for new sensors with only few examples, whether labeled or unlabeled? Now coming to a few specific questions related to deep change vector analysis, where we started the presentation. Here, given these 2 images, X1 and X2, what if this X1, let's say, has only RGB bands, X2 has only NIR bands, that is completely different set of multispectral bands with different resolution, different spectral frequency. Or what if even X1 is an optical image and X2 is a SAR image? And maybe some of you are thinking sorry, I don't know the answer. And that is exactly that another target of my research over here, that is the multi-temporal models. Can they tell me when they really don't know the answer? They should not be just forced to give me an answer because I'm just feeding data to it. They should also be able to tell me when they don't know the answer that, sorry, I don't know the answer. So over here, I conclude my presentation. Before concluding, just a kind of advertisement or something. These are some of the guys that I'm working with currently, with whom I'm getting the opportunity to collaborate on some of the problems that I just mentioned before that we want to cover. And of course, as you see over here, that there is a lot of space left. So if you have some interesting problem on multi-temporal analysis or self-supervised learning or uncertainty analysis, you can always contact me and we can think something out. Thank you.
Thank you, Sudipan, for sharing with us your interesting research topic. Now we give way to questions from our audience. So please, if you have questions, please write the Q letter in the chat or take your turn to speak, please. Is there any questions?
I have a question, if no one else has one. I was wondering about different change and how the models you're developing might be better for different types of change. So particularly I'm thinking about
are you trying to tell us something? We don't hear you.
I think I can hear.
Oh, really?
Yeah, I can hear.
I'm not
Okay,
muted.
sorry.
You can hear? Okay, good. Yes, so I'm asking about different types of change, right? So like in my mind, I'm thinking, is there any difference in kind of the trickiness of the task to look at very immediate change? So say emphasize something like an earthquake where you have immediate change from one time step to the next, and then more slowly creeping change, right? So some morphological change due to I don't know, lens shifts or so, or some change due to long ongoing construction. Are there any particular challenges with these different kind of time lengths of the change?
Mm-hmm. Yeah. Okay. Yes. So to answer your question, first let me go into this framework of this deep change vector analysis again. So this is a kind of like, okay, of course, this first one was proposed for the very high resolution optical, but okay, this more or less similar framework we saw for the some other tasks also, right? So here, one thing that is very important is like the deep feature extractor, okay? So based on like what this deep feature extractor is, like where this is trained on which kind of images, our method will also kind of like this framework will also behave a bit like aligned with this. Like if it is completely trained on the urban area, this deep feature extractor, let's say, probably it cannot give you like changes on like some mining operation, or if let's say it's given on some mining operation or something like that, okay, it cannot give you like the changes related to urban area. This is like type. Now coming more to the timeline, right? The timeline, okay, for like the kind of changes like earthquake and all, what is more always recommended is like to use the SAR version of it because of its better capability to capture the structure, let's say. Which is why like this work is exactly done on like the building change detection in very high resolution SAR images. So when we talk about earthquake, or when we talk about like some other like this kind of immediate changes, okay, even the optical version should be able to capture it based on like, okay, if your change has occurred, and your pre-change image and your post-change images, okay, are like before and after the change. But like let's say like you want to capture something which occurs over the time, probably the version that is more suited is this one, the one that I presented you at the very end, that is unsupervised time series reordering, learning to reorder. Now, because with this one good thing is like this is also kind of able to let's say we are talking about a agricultural area, okay? So in an agricultural area, and let's say you have like 6 months time frame, okay? Like in the 6 months time frame, let's say some changes are very obvious, right? Like there is like a crop cycle, like okay, like in this area, okay, in this months you grow rice, and then you grow like let's say sugarcane. Like these are like common practice, maybe that area. So maybe this is not the change you are interested in, even though that is a change, but that is like something, a natural order of that area. So the good thing about this method is that this method is able to filter out those changes which comes in the kind of natural order, and give you something which is really anomaly, like which doesn't fall in the natural order. So in this kind of changes which have occurred in over the long time, probably in my opinion, this one suits better, because the other ones that we are talking about, they are anywhere like they operate on 2 images at the end. So the assumption is like, okay, you have one before the change, one after the change. Now let's say we are talking about flood, which is actually like one of the case over here in the paper. I've not shown the result here for brevity, but so the thing is, let's say we are talking about flood, right? Like let's say the flood happened over a month, like rain happened, flood happened, and then after some time the area became normal, okay? And you took a pre-change image, let's say in the month of June, you took a post-change image in the month of September, and you see that there was no change at all, because your pre-change image and your post-change image both are perfectly like in a condition without flood. So those kind of bitemporal analysis fails in that kind of situation, where like change can even like slowly disappear also. Whereas in this like in this kind of methods which can operate on the T number of images at a time, or even the one before, they are more suitable for this kind of task, which happens over time. Yeah, I hope I was able to answer your question.
Yes, thank you.
Sudipan, maybe a quick follow-up.
Yeah.
Yeah, first of all, thank you for the very clear presentation and the overview. What I'm thinking with your sequence shuffling, is the aim that you would like to kind of
reduce the sensitivity of your algorithm to the temporal trends and more emphasize on the abrupt changes, let's say, and on the anomalous trends.
Exactly, like not just abrupt, but also anomalies. Yeah, like reduce sensitivity to the changes, like which are anyway the trend, like which most of the time probably we are not interested in. You are right. Yeah, your observation is correct.
Which means somehow that the creeping events are more or less undesired and more or less try to surpass by the algorithm somehow.
Yeah, like the kind of events like which is very much normal in that area, as I gave that example, like this different crops. Okay, maybe in an area this is very normal, like after crop A, crop B comes, after crop B, crop C comes. So okay, like this is probably like not something we are interested in. Like one thing we have to, okay, I showed this image, right? Like otherwise one thing, especially talking about the agricultural area, let's say, which is very normal, is like, okay, sorry, missed the slide. It's like to have like a lot of changes. Like this is a result shown from over the agricultural area, right? And we see like this is the reference map. So like reference map has like a lot of changes, but maybe like, you know, in most of the applications that we'll be interested in, of course, it depends on the application. Probably most of the time, like people, they're not interested to capture those all changes. So yeah, the last method is more towards that.
I see. Thank you.
Thank you.
So Sudipan, I have a question for you.
Yeah.
So in the area of change detection, if you would have the chance to make a wish list, what would be the data sets you would like to have?
You mean wish list?
Yeah. So it does not have to be a data set that already exists.
Yeah, understood. Yeah, so let's come like to it in more in details. Yeah, so like these are like what we showed is like what is next, right? So our data sets that we require are also kind of like applicable to those. Like this first task probably like can be taken like benefit of LCZ42 dataset. So probably, okay, we do not need any dataset at this moment new. But where we need like datasets immediately which are not available is like this case, let's say, like multi-sensor case. We do not have as such much dataset available. So right now I was trying to work with Jonathan and all to have a dataset on like Sentinel-1 and Sentinel-1 and Planet images. So this could be one case, like the multi-sensor, which is very important. Then, of course, the optical and the SAR images. So on this also, I have started working. What we're trying to do is like we have the on-era dataset, which is Sentinel-2, and then we are trying to get the images of the same area, Sentinel-1. But this is just Sentinel-2, Sentinel-1, right? Like the other thing we have to keep in mind is like these deep learning based methods, they become more applicable, they become more fruitful in the analysis of the very high resolution areas. So it will be good like also to have like optical and the SAR change detection, like not just optical and suboptical paired dataset, which I used in one of the work. Change detection dataset, optical and SAR, high resolution dataset for change detection. So this could be another, which is kind of in my wish list. Then another one, which is very seriously in my wish list, is which I did not mention here, is change detection dataset for hyperspectral images. Like right now, we have like I searched over the existing papers and all, and right now I got like only 2 scenes which are publicly available for the hyperspectral. Hyperspectral, I mean not Sentinel-2, I mean really hyperspectral, like hundreds of bands. So currently there are only 2 scenes dataset, One is on is a river data set collected over China, and another one I don't remember right now. So there are just two scenes to evaluate. So it will be really good, like if we have like change detection data set over like for the hyperspectral images, at least 10 different scenes, which should be very useful. And maybe like not just hyperspectral from the same area, maybe when we are collecting over an area, like, okay, we collect also like not just hyperspectral, also the paired very high resolution, so that we can also compare like not just between the hyperspectral, but between multisensor like hyperspectral and the optical, let's say. Then let's say we some interesting case could be for the time series analysis. So one of the cases which at some point strike me very much for the time series analysis is like, okay, let's talk about like for the time series analysis that I already did, of which kind of images I used. This one, okay, sorry that I didn't show you the results, but this one we evaluated on a flood data set and also in a dam disaster data set. But they are like 5 images or 7 images, something like that. Or here you see like some Munich and or the multi-seasons images, Munich or Paris, like that. So rather than that, something which is like more on the application, which strike me at some point, but I could not follow up a lot, is the mining operation. Because there are some areas specifically in the, let's say in the Africa and all, also in the South America, where a lot of illegal mining happens. And it is very important to like monitor these areas. And the evolution is most of the time slow of those areas, because okay, the illegal mines and even for the normal natural mining, I mean lawful mining also, it doesn't happen in like a very fast rate, right? Like, okay, today they do the mining and tomorrow there is nothing. No, not like that. They do it over the months, years and all. So that could be one operation area probably. However, okay, it will always be good like if we have someone who has better knowledge on the mining. Like it would be really good like to collect a data set of like for mining for like a long time series. Other applications can be thought like agriculture, but however, I think there are some already on agriculture, and I probably for the dataset initiative that you have already started. Probably in there also there is some crop cycle datasets as far as I know. So like for the agriculture, of course, there has been more focus, but for the mining, the focus has not been that much, and it would be nice to make a time series on mining probably. So yeah, these are the like currently immediately in my wish list.
Thanks. It's a pretty long one.
Any other questions, maybe?
Maybe a quick comment. Maybe one of the wish lists of Sudipan can be already met, because over South America, we are actually having a project and a lot of data. And we have also thought about thinking about lithium mining in South America with SAR data. So if you're interested, Sudipan, maybe we can follow up on that and see. But you are interested in the amplitude images of SAR, am I right?
Exactly, yeah.
Okay, let's talk about that if you want.
Yeah, I mean, if we have like, let's say if you have the level, we can also get the optical images of this same area.
Yeah, labeling is a little bit of issue, but we can follow up on that if you have interest. Maybe give me a call or something.
Yeah. Thank you.
Sure.
Any more questions, or we still have some more minutes for internal discussions, suggestions of collaboration and so on? Well, if there are no more questions, we say thank you, Sudipan, for this interesting talk, and we keep this talk as concluded. Thank you all the attendants, and we hope we meet us in the next seminars. So thank you and goodbye.
Thank you.